pretty much at this point, we can say that we are expert in finding the magnetic field. But it's not the whole story. It's not enough for the foundation, because if you know how to find electric magnetic field, it's not enough. You also need to know how to describe interactions of these magnetic fields with any object, with any other object, right? And for example, with this, I don't know, clicker or flipper. And so we need to introduce the formula which describes those interactions, which can describe those interactions. And if we talk about interactions, which quantity we need to introduce? Magnetic force. We need to introduce magnetic force, right? And if we want to describe interactions of magnetic field with any object, so we need to present the fundamental formula, right? And if we dive inside of any object, of course we know that it consists of gazillion number of charged particles, electrons, protons, right? So, and if you know how to describe interactions of magnetic field, of any magnetic field, with a point charge, for example, electron or proton, then that can be used as a fundamental formula. And then if you want to describe interactions with some large object, then of course you can apply some logic, some your analytical skills, right? Maybe write the code, and then you should be able to describe, using that formula, to describe interactions with some complicated object. So pretty much the fundamental formula is a formula of describing interactions between a point charge and a magnetic field. So that's what we need to introduce today, right? And once we introduce magnetic forces, then we can say, yeah, foundation is here. So the rest is just application. And then we will see maybe something else must be added, but that will be later. But for now, and we've done exactly the same steps in the world of electricity. Gauss's law, Coulomb's law, which can be used to find electric field, and then we introduce electric force. That's it. That was our foundation. Right. Slides forward. So that's what I told you, right? So the ways of finding electric field, right? And then we added electric force. That was our foundation. Now in the world of magnetism, we're making similar steps, extremely similar steps. Two ways of finding magnetic field, Biot-Savart law and Ampere's law. And now we need to introduce the formula which describes interactions, magnetic force, right? And that is the fundamental one, the fundamental formula, magnetic force on a, and you see, I actually added on purpose moving charge. You remember, I told you a few classes ago that everything is in dynamics in the world of magnetism, right? You remember, in order for a particle to produce magnetic field, it must move, right? It must be in dynamics. It must have a velocity, speed. And now, in order for a particle to experience magnetic force, it also has to move. If particle is stationary, pretty much it's useless, right, in the world of magnetism. It must move every time. To produce magnetic field, it must move. To experience magnetic force, it also must move. Right. Okay, it's a dynamic world. Okay, so that will be the fundamental formula. We will present it, right? And the second formula, which I'm planning to present today, is not fundamental, but really useful, practical formula. Magnetic force on a current, right? And since current is just a bunch of charges, point charges moving in the same direction, so pretty much it means that this formula can be or should be easily derived from this one. So again, this is fundamental, right? And again, when we will introduce Maxwell's equations, a set of Maxwell's equations, this formula, together with a formula for the electric force, will be added to set of Maxwell's equations to form overall foundation of electromagnetism. So this is very, very important formula, right? And again, this is just very practical, right? Because most of the time we deal in our life with currents, not just flying, not just with moving charges. Although there are enough of moving charges. Okay, so let's start with this first. So magnetic force on a moving charge. And as I told you, since it is a fundamental formula, it cannot be derived. It's basically taking as an axiom, right, and written based on experimental results, based on observations, right? A bunch of data, and then you somehow find an expression which can fit that data, right? So it means that can just say, okay, so sort of like a ta-da, and here's the formula, and let's use it, right? Okay, first discuss it, and then we can start using it. So, of course, there must be a point charge because this formula is written for a point charge, right? Point charge Q, for example, let's say positively charged object, which flies with this speed v. And of course, it must be exposed to some magnetic field. So at this particular moment of time, at this particular point in space, there is some value of the magnetic field. Of course, this charge must interact with this magnetic field, and that interaction can be described by this formula. Again, this is the fundamental formula. Sometimes it's called like a Lorentz force. Right? Many books use this term, right? So force on a point charge equals the value of the charge. Okay, just the value of the charge, and then cross product V and B, velocity and magnetic field. You remember I told you that from that point, lots of formulas are going to have cross products, right? And we must be very, very comfortable dealing with these cross products, especially with the right-hand rule. So guys, if you are not comfortable finding the correct direction of the right-hand rule, we can talk after class. You can come to my office hours, or send me email. We can meet outside of office hours. But you must be very comfortable. And plus, it's so simple, right? So just a little bit of mechanics of your right hand, right? But don't wait. Sooner or later, you will have to learn how to use the right hand rule, right? So, so that's the fundamental equation, right? And so how can we find magnitude and direction of this magnetic force? Yeah, now we are experts, right? So magnitude, Q V B times sine of angle between these two vectors, V and B, right? And you remember how to find the correct angle between two vectors. Again, you need to position tails of both vectors at the same point, right? And the angle less than 180 degrees is the correct angle, right? And you know what? Here it's written direction can be found using right-hand rule. Yeah, I just copied and paste from the book, I think, right? But it's not completely correct. It's actually not just one step to find correct direction of the force. I usually call it like 1.5 steps. You have to make 1.5 steps in order to find the correct direction of the force. What do I mean by that? First of all, yes, you have to apply right-hand rule to find correct direction of this cross product. Again, V cross B, and then your outstretched thumb gives you direction of the cross product. But it's not enough. After that, you need to make an additional half a step. You need to look at the sign of the charge. You remember, charge can be positive, charge can be negative. If charge is positive, then yeah, your found direction is the correct direction for the force. But if charge is negative, then you have to what? You have to flip found direction to the opposite one. So first you find the direction of cross product V cross B, and then if charge is negative, you need to flip that direction to opposite one, right? Because that minus in front of the sign of the charge change the direction of the force. I mean, change the direction that you need, right? Change the direction in order to find the correct direction of the force. Okay, it's better to say it this way, right? And guys, of course, I will bug you from time to time about this, and I already did that in the past, and I warned you several times. So here in the world of electromagnetism, forces are sensitive to the sign of the charge. I told you the same about electric force, and now I'm doing the same now talking about the magnetic force. Be careful, because every every semester a few students make these silly mistakes on the final exam, although they know usually, right? But of course they realize, okay, just be more attentive, right? Because then after the exam they would say something like, damn it, how come that I forgot this? Of course I know that. Okay, so check the sign of this charge, of a charge. Okay, so now back to this example. So let's introduce this plane where vectors v and b lie. Why I brought this plane in the picture? Because you need to remember, even before you start applying right-hand rule, you need to realize or remember that cross product, right, all the time perpendicular to both of these vectors v and b. So it means that the direction of the cross product, direction of this new vector, must be perpendicular to this plane, to the plane where these two vectors lie. So pretty much in this case, force must lie along the line which is perpendicular to this plane, and it's a vertical line. So pretty much now the question is, it up or down? Any other direction is impossible, right? You remember the cross product, direction of the cross product is perpendicular to the direction of both of these vectors in the side of the cross product, perpendicular to v and perpendicular to b. Right. Okay, so now let's apply right-hand rule. So first you need to, okay, the wrong direction. Damn it. Every time I'm confused about the directions. Because whenever you use green screen effect, you're seeing everything is on a big TV, big flat screen TV, right? And everything is flipped in front of you. So every time you get confused, where is left, where is right. Okay, so first you need to align your hand along the first vector in the cross product. The first vector in the cross product is v, right? So this. Then you need to orient your hand in such a way so that you can bend your fingers naturally in the direction of B. So I have to do it like this, right? So you see, B is sort of into the screen somewhat. So I have to position my hand like this, right? And my outstretched thumb gives me direction, correct direction for the cross product, V cross B. And then you remember additional half a step. Look at the sign of the charge. In our case, charge is positive, right? So it means that found direction is the correct direction for the magnetic force. So in this case, force is straight up. But if this charge was negative, so magnetic force would be in the opposite direction, down. Right. Although V cross B would be still up, but the force is down. So don't forget about this additional half a step. Okay, so now after this, let's look at a few examples, right? And again, so that is basically after introducing this formula, this fundamental formula. Now we can say, yes, now we presented the foundation of magnetism, right? Once you know how to find the magnetic field, and once you know how to describe magnetic force, that's it. Right. Okay, and for any additional effects, we will discuss later. Right. So now examples. So let's assume that we have this situation. You see magnetic field, blue vectors, right? And you see positive, I don't know, for example, a proton flies along magnetic field lines. Situation, right? You remember, like yesterday, we introduced a solenoid as the object which gives us a uniform magnetic field. So pretty much it's like shooting an shooting a proton along the axis of the solenoid, pretty much through the solenoid. Right? In that case, you remember magnetic field lines are parallel to the axis. So this situation, which is on the slide, is that if you shoot electron through, shoot a proton along the axis of the solenoid. Right? So what can you say about the force, magnetic force acting on this proton? there is no magnetic force in this case, right? Again, so look, this is the formula. So we just need to look at cross product V cross B, right? V that way, B also that way. So both vectors, they are parallel to each other. The angle between them is 0. Two parallel vectors, the angle between them is 0. In the cross product V cross B, we have sine of the angle between them. Sine of 0 is 0. So pretty much it means if you shoot a proton along the axis of the solenoid, it is not going to be deflected because it is not going to experience any magnetic force. Magnetic force will be 0. So pretty much particle is going to fly straight with the same speed and in the same direction. So in this case, magnetic force is 0. But let's change the direction. For example, what if I have here the hole in the solenoid and I shoot a particle basically this way? And in this case, velocity will be perpendicular to the magnetic field lines. The second case, right? So you see, this is basically axis of the solenoid, and now we shoot the particle perpendicular. Now, obviously, magnetic force is not going to be 0, right? So we need to apply our 1.5 steps, or make 1.5 steps in order to find the correct direction of the magnetic force. So first, cross product, direction of the cross product, V cross B. So V is up, right? So you have to align your hand along the vector V. V is up, right? And then you need to orient it in such a way so that you can naturally bend your fingers in the direction of the second vector in the cross product, in the direction of B. So I have to position my hand like this, and you see. And so now I can bend my fingers in the direction of B, right? So as a result, you see my thumb is into the screen, into the page, into the board, right? So but it's on the cross product V cross B, all right? So then additional half a step, sign. Look at the sign of the charge. Charge is positive, so found direction is the correct direction for the magnetic force. So in this case, force is into the page, point into the page. Now this situation. So a magnetic field crosses. Crosses means, you remember notation. Cross means magnetic. Okay, the vector is into the screen, is into the board. Dot out, right? But cross is in, right? And particle again positively charged flies this way. So what's the direction of the force? Again, right hand rule, and then look at the sign of the charge. So first I need to align my hand along V, right? All right, so like this. But then you need to orient it so that I have to orient it so that I can naturally bend my fingers in the direction of the B. So I have to position my hand like this, right? It's still along V, but now I can bend my fingers into the board along B, right? So you see. Yeah. So that's now correct position of my hand in order to find the correct direction of the cross product V cross B. So my thumb gives me direction upward direction, right? So that's the direction of a cross product, and since charge is positive, so that's the correct direction for the magnetic force. Magnetic force. So in this case is up. Again, guys, at home, practice that, right? And again, don't be scared. Come to an office hours. It's not a rocket science. It's quite simple. So last example. What if we have this situation? Again, magnetic field lines. Magnetic field is into the screen, and particle flies this way. So like in the previous example, first you have to find direction of the cross product. V cross B, right? And cross product V cross B is up. But half a step, Q is negative. Charge is negative, you see? Charge is negative. So it means that now I need to flip found direction to the opposite one. So magnetic force is going to be straight down. Since Q is negative, force will be down. So this particle is going to fly some kind of, will have some parabolic motion with a branch down. Right? But here in this case, it will be some kind of a parabola, most likely with a branch up. There will be, I think, a couple of questions of this type in your homework. I added conceptual questions from from the end of the chapter. Right? So you have to practice. And guys, if you're not comfortable, come to me. You shouldn't struggle with finding directions. It's not that complicated. So now, a couple of questions for you. We have magnetic field created by this permanent magnet. Again, you remember magnetic field lines looks like they start on positive charge, and it looks like they start on the North Pole, right? And on the South Pole. But you remember, it looks like, because all the time magnetic field lines form closed loops, right? You remember, it's a consequence that no one has ever observed magnetic monopoles. So pretty much all these magnetic field lines are connected through this permanent magnet. Then we have a positive positive point charge, right, flying that way. So direction of the magnetic force on that proton, and you see options. Okay, give it a try, and of course the formula is here. Right? So number of responses is not growing, so it means that now it's time for me to discuss. Pretty much not much to discuss, right? So we just need to explicitly show direction. Just show the vector, the second vector in this cross product, vector B, because we see magnetic field lines, but we know how we can find magnetic field vector based on magnetic field lines. Magnetic field vector is tangent to those lines, right? So at this point, I need to bring slides forward again. So at this point, of course, magnetic field is going to point this way. And so now, first, you need to find the cross product. And since charge is positive, so that direction of the cross product is going to give us the direction of the magnetic force. So first I need to position my hand, align my hand along vector V. V is straight up. So sort of like this, right? So, and then I need to orient my hand and position it like that, you see? So that I can naturally bend my fingers in the direction of B. B is that way, so you see my fingers also that way. So like this, like that, and so my thumb is out of the screen, right? Out of the screen. So it means that that is the correct direction of the magnetic force. Dot, dot. You remember notation? It means out of the page. It's like an arrow flying. That's what you see when an arrow flies towards you. Out of the screen, so D. Right. Okay, the next one. Something similar, but now what if we have an electron flying that way? Again, the same question, basically, what can you say about the magnetic force in this situation? Or actually, it asks for magnetic force, direction of the magnetic force. But also there is an option of magnetic force is 0. In this case, actually, it's much easier. We still need to see direction of the magnetic field, right? Direction of the magnetic field, of course, will be that way. Again, slides are behind. So direction of the magnetic field that way. So V that way, okay, B that way, V that way. So they are anti-parallel. So what's the angle between them? 180 degrees, right? 180 degrees. So if you write magnitude of this force, QVB times sine of angle of 180 degrees. Sine of 180 degrees is 0. Right. So it means, of course, that force is 0. So it means that this particle is going to fly in that direction forever and ever without changing its velocity and changing its direction. So since force is 0. Okay, good. Now, enough about the fundamental equation. Next class, we will talk about some beautiful phenomena, very interesting phenomena, but that will be next class related to that fundamental formula. But for now we need to introduce that practical formula, magnetic force acting on a wire with a current. Right. But again, now this formula, it's not fundamental. It's but very, very practical, because in our life we have tons of currents, right, which can be exposed to the magnetic field. And of course, we can ask ourselves that question. So will they experience any magnetic force? Okay, so let's assume that this is a piece of wire. It doesn't have to be straight. It can be of any shape, right? Completely any shape, right? And of course, there's a current flowing through this wire, right? Of course, it must be exposed to the magnetic field, because otherwise it would never experience magnetic force, right? And of course, the formula which we need to present is derivable, can be derived from this. Again, this is our fundamental formula on a point charge, but if you have a bunch of identical charges drifting in the same direction, of course, this derivation, this transition from this formula to the formula which we want to present should be very straightforward. But we're not going to do it because it will take us, I don't know, 10 minutes or so, but still straightforward. And I don't feel like deriving that because it's mainly simple logic. So, but anyway, first of all, which formula we have to present? Look, since we're talking about a wire of a completely arbitrary shape, right? And of course, it is exposed to a magnetic field which is not uniform, right? It's like that's what I show on the picture. Right? It means that different pieces of wire are in different conditions, different magnetic field, different directions of the current, and so on and so forth. So pretty much we cannot write down the formula for the whole magnetic force on the whole wire, right? So we have to present a formula in a differential form, right? So we need to take a small section of the wire and write the formula which describes magnetic force acting on that infinitesimally small section of the wire. So in the differential form, right? So it means that we need to take, for example, this small piece of wire with the current, right? DL. And at this point, you should start screaming at me and I know the author of the book, right? Because all the time, okay, I will continue introducing the formula in a second. It just at this point, every time I felt so awkward, so weird, because you notice in this book, whenever we talked about some wires or some directions, every time we use ds to denote infinitesimally small section of the wire or the path, right? DS, all the time it was DS, and now suddenly DL. I don't like books where authors do that when they change notations from chapter to chapter. Right? It's annoying. It's really annoying. But in this situation, I think the case is that there are some classical books in physics, like John Cawley, for example. It's considered to be classical, right? All right. And then when different authors start writing their own books, they try to be different. They try to introduce different notations, right? Like in this case, like instead of DL, author used DS, right? But when they come to this point to write this formula, which I'm going to show in a second, it's sort of like an unwritten convention. You can open any book and everywhere DL is used. DL, not any other symbols, right? So when all these authors come to this point, they suddenly flip from DS, for example, to DL, right? In this case, and it's again, it's not a crime, but it doesn't sound cool. It doesn't look cool, right? These flipping notations. But anyway, it's not a crime. You can easily realize and follow what is going on here, right? So, but anyway, DL. right? Not ds, but dl. And again, you see it presented as a vector. What determines direction of this dl? Direction of the current. There's only one direction in this wire, direction of the current. So that direction determines direction of dl. Right? If current that way, so that will be direction of dl. If current this way, that's the direction of dl. Right? Okay, so and the formula will give us magnetic force acting on this small section of the wire dl. Tada. You see, df, as I said, differential form, right? So the value of the current and then the cross product of dl, again, direction of dl is determined by the current. And crossed, it is crossed with b. So now, again, you see the cross product, as I promised to you, that from that point, we have almost every formula. Every formula has a cross product. Again, magnitude, it's a I dl times b times sine of angle between these two vectors, but then direction. Direction, now it's a one step, not 1.5 step like in this case, because here current cannot be negative. Current is just the value of the current, right? 5 amps, 3 amps. In this case, current cannot be negative, right? In this case, it's just the absolute value of the current. So if you found a direction of dl cross b, that's the direction of the magnetic force acting on this section of the wire dl. Okay, then, but you know what? I don't think that we're going to use this formula that often. We're going to simplify it, right? We're going to adjust this formula, apply this formula for this special case, for a straight wire. Not just of an arbitrary shape, right? Straight wire. Because most of our wires, right? Not most, but quite often we see the situation. So let's adjust this formula for a special case, for a straight wire. But in this case, the wire doesn't have to be infinitely long. Okay, it can be, for example, let's say this is an infinitely long wire, but let's say only this length L of the wire is exposed to the magnetic field. Only here we have magnetic field. And let's assume for simplicity that magnetic field is uniform, right? I just checked the time to make sure that we're in a few minutes I will stop the lecture and we'll switch to the exam. And let's assume that magnetic field is uniform. Then transitioning from this formula to this particular case is very simple. You just need to integrate this over this length. And since current is the same, magnetic field is uniform, also constant, so pretty much you just need to integrate this dl. So if you integrate this dl, you will just get the total length of this piece of wire which is exposed to the magnetic field. As a result, you will get the net force acting on this piece of wire of length L is basically, you see the structure is almost identical. Instead of dl, we have just L. So I, L, cross B. So where L, again, direction is determined by the direction of the current, and L, magnitude of L, is just the length of that piece of wire which is exposed to the, in this case, uniform magnetic field, right? So this formula, we're going to use many times. So this and the fundamental formula. And again, you remember, this is fundamental, and this can be easily derived from the first one. But from the practical point of view, this is very useful, and as this one. Okay, let's look at a couple of pictures, examples. Right. Here. So what if we have this situation? You see, we have a wire, vertical wire with a current is up, and these blue vectors, light blue vectors, also up, magnetic field. So what can we say about the magnetic force acting on this wire? Magnetic force will be 0. Because in this case, in the formula, every time we have what? Cross product of L vector, and direction of the current determines that direction of L. Right? So when you take a cross product of this L and magnetic field, they are both parallel, both up. So angle between them is 0. So sine of 0 degrees is 0. So in this case, magnetic force is 0. So in this case, this wire is not going to experience any magnetic force. Again, as I said, direction of L is determined by the current. L is up. magnetic field is up, cross product of two parallel vectors is 0, or 0, right? Yeah, something like this can be on the among conceptual questions, right? On the exam. Now, oh, I flipped in the wrong direction. So, but in this situation, you see, I turn magnetic field direction by 90 degrees. In the previous slide, magnetic field was up. Now magnetic field is into the screen, you see, crosses. So now angle is 90 degrees between L and B. Right, so L again is determined by the direction of the current, so L is up, B is into the page, so L cross B, so that's the correct orientation of the hand, right? And as a result, my thumb gives me the correct direction of the magnetic force. Magnetic force is this way, right? And again, in this case, current cannot be negative. This is just the absolute value of the current, so direction of L cross B actually gives us direction of the magnetic force immediately. Right. Okay, so that's basically the foundation. I keep reminding about this foundation. So you see what we have as a foundation in the world of electricity. Coulomb's law with the probe charge that can be used to find electric field, Gauss's law to find electric field. So these are options of finding electric field. And then once we added electric force, this is the foundation in the world of electricity for now. And similar things are now we introduce in the world of magnetism. Biot-Savart law can be used to find magnetic field. Ampere's law can be used to find magnetic field, two ways of finding electric field, both fundamental, equally strong, and so on and so forth, right? And then once you add this Lorentz force of magnetic force acting on a charge, so now this is the foundation of magnetism, right? So you see similarity. And of course, this is very practical. It's not a fundamental equation, but very practical. So the foundation is up to this point. And you see, we have similar foundation in both of these worlds. We'll see in a few classes what else can be added, right? So, but that will be later, right? So, but for now, yeah, that's the foundation. So from this point, yeah, we'll just start applying these fundamental formulas in the world of magnetism to describe some particular situation.